In this video, we are going to continue our discussion of Green's theorem, but focus on flux for this problem. Find the outward flux of the vector field, all right, and I'm going to go ahead and label these Mn, across the boundary of the annulus. Now we're talking about a full annulus, in which, when expressed in polar coordinates, is the set, and they even gave us the polar coordinates, so when we get to our integral, we know we're going to switch to polar. We know that from the last problem, the annulus calls for polar, makes it much easier than trying to think of it in rectangular. Okay, so flux definition, let's remind ourselves of that before we start. We're not putting an F there, but path C of some vector field. And we're dotting it with the in vector that was described when we talked flux. Remember, that is a vector that we have our tangent unit vector, and we have an in that sticks out orthogonal on the right side of the path. So if we were running across our path, it's always on the right side. Okay, so this, according to Green's theorem, though, we can change to the partial of m with respect to x plus the partial of n with respect to y dA. Okay, but we have to confirm a few things about C and R. I'm going to go ahead and do R first. Let's call this C1 and R1 because we're going to actually have to think about this differently. Let's think about R being connected first. Right? R being connected. Right, that means I can put any 2 points I put in R here. If I put one here and here, I can connect them. It is connected. Now, but simply connected, I have that hole in the middle. If I put an open set like that, I can't contract it down to a point that is in C. So I can't think about it this way, right? But we can actually do it a different way and think about a different path. Now, this is going to be kind of silly because it's not really going to change the way we do anything in our calculation. It's just going to work out, but we do have to confirm it to make sure we can even use the theorem. What we can do instead is think about running across there. We see these two boundaries here. We can actually get really close to this boundary right on it, or right on it actually would work. So if we started right here and we went counterclockwise and we went around like this, and we go around the circle, and then we go back over this line, and we go underneath and come back around to that. That would actually satisfy our R regions if I do that and break it up. It is still connected. 2 points, I can connect them in R. That's not too hard to satisfy. But the simply connected, now I can't draw it around the hole because there's a boundary there. So it would have to be like some boundary like this, right? And that boundary does contract down into C. I can't make it go all the way. Now, the simple and closed, I pulled this from a few textbook does this problem. So a few different textbooks do this problem. I agree that it is closed for sure. The simple, it just depends on how you define it crossing over each other. Now, why this doesn't change the problem, we really didn't answer. It's because we have one way going like this, the orientation, and the other way the orientation's going like that. So when I'm running across that same line and I'm adding up my vectors, right, adding up my density, or the flux across that, we're not talking circulation or density anymore, but flux across that, this way and that way would both just cancel out with each other. I'd have positive flux going one way, and then since flux works the same way because it's based on the vector field, not the path, the flux, right? Or it's based on the path in which way it's going, but if that line is the same, the orientations would just cancel it out because I would pick up the same kind of forces, one being positive, one being negative. So if we squint our eyes enough, I believe it's simple. I'll take the textbooks, their words for it. I could argue that running over the same line is actually intersecting each other, which means it wouldn't be simple. But we're going to go ahead and trust the textbooks. If you have some kind of explanation that you think would be valid, I wouldn't mind an email if you got the time. So, but we'll just take it, and let's go ahead and do our flux. All right, so outward flux. Remember, this is like a crosswind. Is the closed over the closed simple path C of our vector field dotted with n. ds is the same thing as the vector field C, and I'm going to go ahead and fill these in. xy squared dy minus x squared y dx. That's the definition of that. And we know we can now use Green's theorem here and do it over a region R. And it's going to be dm dx plus dn dy dA. So we need those two partials. So we have the partial of m with respect to x. Okay, if I look up here, m was xy squared, so that is just a y squared. If I do the partial with respect of n with respect to y, that is x squared y, so the y just goes away and I get an x squared. This becomes the region, or the double integral over region R of x squared plus y squared. We can flip it either way, and then dA. Well, this calls for polar, again, not polar, because the annulus, and they even described it in polar force up here, so here are bounds. All right, so let's write that out. We have theta was 0 to 2 pi. That's all the way around the annulus. Then it was r, I think it was 1 to 2. Yep, 1 to 2 in this case. And then x squared plus y squared is the same thing as r squared. And then we change to polar, so we have r d theta. That is a very simple integral to solve, so I will leave that up to you. This is 5/2 pi. So that is the measurement of the flux. That means going across the annulus, and we could even look at that picture. And taking a look at our picture there, we can go through and see that we have a lot of vectors in every single corner going this way, right? Every single corner, I have a lot of flux going across from left to right. And especially even when we go back into the little, right? We go across here and go around this path. The inside of it, we're getting a lot of left to right. So it makes sense that we get some number that is a big positive number, because we had a lot of force going from left to right over our path.